reggelt kívánok, hölgyeim és uraim! Szeretettel köszöntök mindenkit itt a Hunren, Rényi Alfréd Matematikai Kutatóintézet nagytermében, és egyúttal a MTA YouTube csatornáján is azokat a nézőket, akik nem tudtak ma eljönni, de a távolból követik a mai programunkat. A Stipsic András igazgató úr sajnos konferencián külföldön van, nagyon sajnálja, hogy nem tud részt venni a mai rendkívüli eseményen, de engem kért meg arra, hogy köszöntsem vendégeinket. Mindenek előtt nagy tisztelettel és szeretettel köszöntöm Fuchs László, a Magyar Tudományos Akadémia külső tagját, aki ebben a hónapban fogja betölteni 100. életévét. Köszöntöm Freund Tamást, a Magyar Tudományos Akadémia elnökét, Hudec Ferencet, az MTA alelnökét, Páles Zsoltot, az MTA Matematikai Tudományok Osztályának elnökét, és Kacskovics Imrét, az ELTE TTK dékánját. I very warmly welcome our speakers today. There will be 5 mathematical talks after the ceremonial part of this event. And I'm very happy that they accepted our invitation. So I warmly welcome Professor Luigi Salce from Padova, Berkes István Budapestről, Professor Miroslav Hušek from Prague, Professor Norbert Ortner from Innsbruck, and Professor Ludwig Reich from Graz. The first part of the program will be in Hungarian, and our foreign guests got some translation of some previous remarks of László Fuchs, which he made 10 years ago when we celebrated his 90th birthday, and also some excerpts of his CV and a description of the prize he will receive in a few moments. So if there are someone else who needs the English translation, there are a few more copies left, but then we start with the Hungarian part of this event, and the first Zsolt Páles, the chairman of the mathematics section of the academy, will address you.
Tisztelt Hölgyeim és Uraim, kedves kollégák! Egy nem mindennapi esemény miatt gyűltünk ma össze. 5 világhírű matematikus 100. születésnapját ünnepeljük. Ez alkalomból örömmel és tisztelettel köszöntöm Fuchs László professzor urat, az MTA külső tagját, a Nagy Ötös, a Big Five egyetlen velünk ünneplő tagját, továbbá Freund Tamás professzor urat, az MTA elnökét, Hudec Ferenc alelnök urat, az MTA alelnökét. Köszöntöm továbbá természetesen az ELTE természettudományi karának dékánját, ő is velünk van a mai alkalommal. Köszöntöm ezen túlmenően a mai tudományos előadássorozat előadóit és a megjelent vendégeket is. Ha az interneten rákeresünk a Big Five kifejezésre, ezt tettem ugyanis az elmúlt napokban, akkor rábukkanhatunk a pszichológiai személyiségvizsgálattal kapcsolatos Big Five elméletre, vagy az 5 legnehezebben levadászható afrikai vadállatra. Nekünk matematikusoknak azonban nem ez az elsődleges jelentése ennek a kifejezésnek, ennek halattán többségünknek 5 matematikus neve jut az eszünkbe: Aczél János, Császár Ákos, Fuchs László, Gaál István és Horváth János. Egyikük, Aczél János, a 2004-ben Sztár Gyulának adott interjújában, amely csak 10 évvel később, 2014-ben jelent meg a Természet világában, így val a Big Five történetéről. Bár ugyanabban az évben születtünk, mégsem ugyanarra az évfolyamra jártunk. Én decemberben születtem, így már az elemi iskolától kezdve évvesztesnek számítottam. Az egyetemen abban az időben nem volt sok matematika iránt elkötelezett hallgató, így mi 5-en hamar egymásra találtunk. Van ebben némi bizonytalanság, mert nem ugyanúgy emlékezünk a kezdetekre. Azt a változatot mondom, amellyel többen értünk egyet. Bár az egyetemen jó tanáraink voltak, de a matematika számos területe fehér folt maradt az oktatásunkban. Az életünk pedig nem tűnt elég hosszúnak ahhoz, hogy kivárjuk, amíg ez megváltozik. Különben is fiatalon minden olyan sürgős az embernek. Valamelyik külső szervezet, talán a Magyar Demokratikus Ifjúsági Szövetség, rövidítve MADISZ, szervezett olyan előadásokat, amelyeken a társaiknál valamivel többet tudó diákok beszéltek a matematika őket érdeklő új területeiről. Így kezdődött. Akik ott diákként előadtunk, többségünkből elég jó tanár lett. Mégis akkor néhány hét alatt sikerült kipusztítanunk a teljes hallgatóságot. 5-en maradtunk. Mi azután is rendszeresen összejöttünk, de már csak egymásnak magyaráztuk, hogy ki mind dolgozik. Arra határozottan emlékszem, hogy évenként egyszer nyilvános ülést is tartottunk, amelyre bárki eljöhetett. Egyes emlékezők szerint Fejér Lipót volt a keresztapánk, ő nevezett el minket Big Five-nak. A Big Five fénykora 1946-47-es tanévben kezdődött, és 48 őszéig tartott. 47-ben mindannyian doktoráltunk, Fejér Lipót akkor már nagyon öreg volt, bár ha belegondolok, jóval fiatalabb, mint én most. Ez ugye 2004-ben készült ez az interjú. 1944-45-ben történtek, azonban nagyon megviselték Fejér Lipótot. Legtöbbet akkor lehetett tőle tanulni, amikor nem tanított, hanem a dolgok hátteréről beszélt, hogy mi mivel függ össze. Azokról a nagy matematikusokról mesélt, akiket személyesen is jól ismert. Fuchs László egy a Magyar Tudományban megjelent cikkében pedig így emlékezik vissza. Összejöveteleig nem csak abban különböztek a közönséges szeminárium előadásoktól, hogy állandóan közbevágtunk kérdésekkel és ötletekkel, hanem abban is, hogy szinte megállás nélkül nevettünk és tréfáltunk. Aczél János volt a legtöbb vicc szerzője, de a tréfálkozásban mindegyikünk nagyon is aktív volt. A tréfa tárgya többnyire a tárgyalt téma vagy annak tálalási módja volt. Csodálatos, hogy a sok tréfa mellett komoly matematikát tudtunk tanulni. Talán a legjellegzetesebb tevékenységünk a plakátkészítés volt. Számos összejövetel után a legviccesebb helyzeteket rögzítettük plakát formájában. A plakát meghívó formájában készült, meghívóként a lezajlott előadásra, mintha előre tudtunk volna a vicces eseményeket. Az előadások helyét mindenkor Lipót mezőként jeleztük, hivatkozással Lipi bácsira, és a közismert Lipót mezei elmegyógyintézetre. Mindegyikünknek más neve lett, például Gál Pista, Loglog Pista néven szerepelt. A plakát szerkesztéshez mindegyikünk hozzájárult ötleteivel, és az én feladatom, mármint hogy Fuchs professzor úr feladata volt, a végleges forma megszerkesztése, Aczél János közreműködésével. Én jó magam a Big Five kifejezést és annak igazi tartalmát 20 évvel ezelőtt, 2004. júniusában ismertem meg, amikor először került megrendezésre Magyarországon egy velük kapcsolatos esemény, 400 év matematika címmel. Ezen akkor a 80 éves Big Five tagok még mindannyian tartottak előadást. Felsorolom az előadókat és az előadásuk címét. Horváth János, Visszapillantás az elmúlt 62 évre címmel, Aczél János, Mi a teendő, ha egy függvényegyenlet érvényességi tartománya túl kicsi, Fuchs László, Ábel csoportok és modulusok, Gaál István, Mikor periódikus egy Fibonacci sorozat, Császár Ákos, Természetes operációk általános topológiákon, Horváth János pedig a Riesz-Fischer tételről beszélt. 2014-ben, 10 évvel később, a 90. születésnap megünneplésére már csak Aczél János és Fuchs László tudtak eljönni, a többiek nem tudták vállalni a megterhelő utazást. El kell mondani, hogy a Big Five tagjai a II. Világháború utáni időszakban fontos szerepet játszottak a hazai matematika újraindításában és nemzetközi szintre emelésében. Sokat tettek a magyar matematikusok nemzetközi kapcsolatrendszerének bővítéséért is. Életük során mindvégig szoros baráti kapcsolatban maradtak, annak minden lényeges fejleményéről informálták egymást, és folyamatosan figyelemmel kísérték egymás életpályáját. A Big Five tagjainak hatása csak nem felmérhetetlen. Túlzás nélkül mondhatom, hogy nincs ma Magyarországon olyan matematikus, aki első éves egyetemista korában ne forgatta volna Fuchs László Bevezetés az algebrába című tankönyvét. De Aczél János függvényegyenletekről és Császár Ákosnak a topológiáról írt könyvei is a tudományterületük bibliájává váltak. A mai tudományos ülésszak keretében az előadóink segítségével megpróbáljuk feleleveníteni a Big Five tagjainak lényeges eredményeit, életútjuk legfontosabb állomásait. Remélem, hogy a megjelent hallgatóság is sokat profitál majd az elhangzottakból. Mindenkinek kellemes és tartalmas ismeretszerzést kívánok, és ezekkel a gondolatokkal a mai ülésszakot megnyitom. Köszönöm szépen.
A Magyar Tudományos Akadémia, a Magyar Tudományosság Külföldön Bizottsága által megalapított Arany János díjat különböző kategóriákban adja át. A legjelentősebb ezek közül az Arany János életműdíj. Ezt ebben az évben Fuchs Lászlónak ítélte oda az akadémia. Megkérem Freund Tamást, az MTA elnökét, a laudáció elmondására.
A matematikusok sokáig élnek. A matematika egy egészséges hivatás. Tisztelt professzor úr, kedves akadémikus társaim, hölgyeim és uraim! Azt hiszem, nem kell túl sok eszköz ahhoz, hogy ma ezt az állítást bizonyítottnak fogadjuk el. Matematikusok sokáig élnek, a matematika egy egészséges hivatás. Az egyik bizonyíték, hogy az idézett gondolat Dirk Jan Struik holland matematikustól származik, aki 106 évet élt. A másik, hogy az idei Arany János életműdíjasunk, az életműdíj átadása egy 100. születésnap ünneplése is egyben. Tudom persze, hogy az élet törvényei ennél árnyaltabbak, hiszen elég, ha csak a Matematikai Kutatóintézet korán elhunyt névadójára, Rényi Alfredra gondolunk, de az ünnep fényében engedjék meg nekem, hogy ma az egészséges hivatást űző matematikusok hosszú életére, és különösen Fuchs László több mint 3/4 százada töretlen tudományos aktivitására fókuszáljak. Kedves ünneplő közönség, 20 éve hagyomány immár itt a Rényiben, hogy 10 évente köszöntjük a legendás Fejér Lipót által Big Five-nak nevezett, szintén legendás magyar matematikusokat, Aczél Jánost, Császár Ákost, Fuchs Lászlót, Gaál Istvánt és Horváth Jánost, és tisztelgünk munkásságuk előtt. Ez a mostani tehát a harmadik ilyen összejövetel. 10 évvel ezelőtt, 90. születésnapjukon a magyar matematika nagy ötös fogatának, ahogyan Lovász László nevezte őket, tagjai még mindnyájan meghívottak lehettek az ünnepségre. Akkor mondott köszöntőjében Fuchs László így fogalmazott: legyen szabad megköszönnöm Big Five-éreim nevében is a bennünket ért megtiszteltetést, hogy a Magyar Tudományos Akadémia matematikai osztálya ezt az ünnepi rendezvényt szervezte 90. születésnapjaink alkalmából. Mély hálával tartozunk. Kedves professzor úr, mi tartozunk mély hálával. Miénk volt a megtiszteltetés 10 éve is, és miénk most, amikor 100. születésnapján köszöntetjük, és több mint 75 éve folyamatosan végzett tudományos munkássága iránti tiszteletünkkel átadhatjuk önnek az Arany János életműdíjat. Bertrand Russell Study of Mathematics című eszéjében így ír a matematikáról: a matematikát, ha helyesen fogjuk fel, nem csak igazság, hanem egyszer, mint magas rendű szépség is jellemzi. Hideg és szigorú, a szobrászatihoz hasonló szépség, fenségesen tiszta, és oly szigorú tökére képes, amilyen csak a legnagyobb művészet tud felmutatni. Henri Poincaré pedig így fogalmazott: a matematika olyan nyelv, amelyen nem lehet ködös vagy pontatlan gondolatokat kifejezni. Mi az tehát, amiért a matematikusok, ha az élet más törvényei másképp nem rendelik, sokáig élnek? Talán éppen a tisztaságnak, a tökének, a rendnek ez a szenvedélyes keresése, szeretete. Amit a pályája kezdetén, 1947-ben megjelent 4 angol nyelvű cikkétől kezdve, egészen a tavaly megjelent 2 publikációjáig, és a most is folyamatban lévő munkáig Fuchs László is példaként elénk él és képvisel. És képviselte és képviselték Big Five-éreivel akkor is, amikor ezt a történelem árnyékában kellett tenniük. Amikor a háború után 1945-ben önszervező erővel hétről hétre 5-en összeültek, és a kellemes matematikának kemény munkával átadták magukat. Up-to-date matematikát tanultak, és megkövetelték önmaguktól, hogy mindig valami újat is hozzátegyenek ahhoz, amit olvastak. És néhány év alatt újraindították, és ismét nemzetközi szintre emelték a magyar matematikát. És azt szerették és képviselték, bárhol is éltek, vagy adtak elő az 5 világrészen. Tisztelt Hölgyeim és Uraim, kedves ünneplő közönség! Arról, hogy a történelem milyen súlyokat tesz ránk, személyesen legtöbbször nem tehetünk. Ez nem a mi döntésünk, kívülről ér minket. De hogy abban a helyzetben, amelyben vagyunk, mit teszünk, hogy helyzetünkhöz hogyan viszonyulunk, az elsősorban a mi kezünkben van. A belső szabadság és a hivatásunk iránti hűség mellett, munkánk minőségi volta mellett tudunk dönteni. Fuchs László és a Big Five tagjai egyetemi éveik idején így döntöttek. A matematika iránti odaadó szeretet végigkísérte életüket, és munkásságuk megajándékozta a nemzetközi és magyar tudományt. Tisztelt professzor úr, Turán Pál egyik cikkében ezt a gondolatot idézi Rényi Alfrédtól: ha boldogtalan vagyok, matematikával foglalkozom, hogy felviduljak. Ha boldog vagyok, matematikával foglalkozom, hogy az is maradjak. 100. születésnapja és az Arany János életműdíj elnyerése alkalmából Rényi Alfréd nyomán azt kívánom önnek, hogy boldog legyen, és az is maradjon.
Köszönöm szépen, elnök úr, és megkérem Fuchs Lászlót, hogy köszönő beszédét mondja el.
Mélyen tisztelt elnök úr, kedves kollégák és vendégek! Hálásan köszönöm a rendkívüli megtiszteltetést, az Arany János életműdíjat. Nagyra értékelem ezt a nem várt magas kitüntetést. Köszönet Freund Tamás elnök úrnak, Kocsis Károly akadémikusnak és a matematikai osztálynak ezért a nagyon megtisztelő elismerésért. Mielőtt néhány szót szólnék életpályámról, nem mulaszthatom el, hogy ne idézzem fel mély hálával szüleim emlékét. Édesanyámnak sikerült átültetni apjától örökölt lappangó matematikai tehetségének egy töredékét. Édesapám egyik vezető finnugor nyelvész példát mutatott állami elismerés hiányában is a nagy áldozatokat követelő önzetlen kutatómunkára, alapvető tudományos kérdések vizsgálatának fontosságára. Az ő hatása életemre mérhetetlenül nagyobb, mint mindenki másé. Fiatalon, 14 éves koromban kezdtem komolyan érdeklődni a matematika iránt. Egy régi geometriai tankönyv anyagát alaposan tanulmányoztam, de csak utolsó gimnáziumi évemben jutottam komoly anyaghoz. Ekkor lettem jó probléma megoldó Gallai Tibor jóvoltából. A numerus clausus miatt nem vettek fel a műegyetemre, de félévi gyári munka után beiratkozhattam a bölcsészkarra, mint matematika-fizika szakos tanárjelölt. 1945-ben, közvetlenül a háború után a Pesti Egyetemen nem lehetett sok matematikát tanulni. Fejér professzor nagyon legyengült a német megszállás alatt, kerékjáró professzor betegsége miatt már előadni sem tudott, csak 100 Pál docenstől tudtunk tanulni. De ő nem dolgozott doktorjelöltekkel. A katonai szolgálat, a szörnyű hadifogság és az embertelen munkaszolgálat okozta háborús szenvedések nem tört meg bennünket. Elhatároztuk, hogy együtt tanulunk komoly matematikát. 5-en, mind az 1924-es születésűek jöttünk össze a nyáron, és hetente találkoztunk a tanévben. Egyikünknek sem volt tanácsadója, de egy év múltán mindegyikünk dicsekedhetett közelkész disszertációjával. Van der Waerden nevezetes modern algebra könyvének hatására kezdtem ideál elmélettel foglalkozni. Engem Emmy Noether leghíresebb, alapvető matematikai cikke vonzott, és az ott bizonyított 4 analóg tételhez egy 5-et találtam. Ez lett disszertáció fő eredménye. A rendezett algebrai struktúrát elmélete kezdett érdeklődni, de nem sokáig maradtam ennél a témánál. Szoros barátság fűzött Szele Tibor debreceni professzorhoz, aki egyre nagyobb lelkesedéssel szólt Ábel-csoportokról és saját eredményeiről. Mindig említett érdekes, megoldatlan problémákat is, amelyek felkeltették érdeklődésemet, és hamarosan én is Tibor kutatócsoportjához csatlakoztam. Szele tragikus korai elhunyta nagy csapás volt, de jó ideig Magyarország maradt az Ábel-csoportok elméletének nemzetközi központja. A Matematikai Unió bennünket bízott meg egy nemzetközi Ábel-csoport konferencia szervezésével. Ez maradt kedvenc témád is egész életemben. 3 könyvet írtam Ábel-csoportokról. Az Ábel-csoportok elméletének rohamos fejlődése inspirált Salce páduai professzorral közös programunkat. Az új, hatásos módszerek szisztematikus átültetését és továbbfejlesztését terveztük modulusukra, integrálási tartományok felett. Számos cikket és 2 könyvet publikáltunk az új eredményekről. Hosszú időn át dolgozatim témái főként az Ábel-csoportok, modulusok, gyűrűk és a rendezett algebrai struktúrák elméletéből választottam. Talán hibát követtem el, hogy gyakran váltottam kutatási problémáimat, de megvallom, nem tudtam ellenállni annak, hogy egy felmerült érdekes problémát ne próbáljak megoldani. Már 80 éves voltam, mikor nyugdíjba mentem, de a matematizálást semmiképpen nem tudtam abbahagyni. Az elmúlt 20 év alatt számos régi problémáról írtam, és több érdekes kérdést tisztáztam számomra új területen, a kommutatív gyűrűk új ágában. Örömmel állíthatom, hogy sikerült bizonyítanom egy fontos egzisztenciatételt. A tétel: matematika létezik 90 év után is. Ez nem új tétel, de abban egyetértetünk, hogy ezt nem könnyű bizonyítani. Elterjedt szokás elismerés alkalmával ígéretet tenni a jövőbeli munkára. Az én koromban ennek nincs értelme, de azt nyugodtan állíthatom, hogy kitüntetésem megerősít abban a törekvésemben, hogy bizonyítsam, matematika létezik még 100 év után is. És ebben maradunk. Köszönöm szépen!
egy meglepetés is következik. Felkérem Kacskovics Imre dékán urat ennek átadására.
Tisztelt professzor úr, dékán úr, tisztelt elnök úr, osztályelnök úr, alelnök úr, hölgyeim és uraim, kedves kollégák! Én nagyon megilletődötten állok itt, és örömmel. Fuchs professzor, ahogy hallottuk, 1946-ban végzett, 22 éves korában. Ahogy hallottuk, nem könnyű körülmények között. 47-ben már doktori fokozatot is nyert. 49-ben az ELTE alkalmazottjává vált, és 54-től 56-ig az ELTE matematika, kémia, fizika karának a dékánja volt. Ez érdekes, mert egy időben volt egy másik matematikai intézet és egy másik kar is, ami aztán összeolvadt. Elég nehéz időszak lehetett ez akkor is. Egy másik korábbi dékán születésnapi ünnepségére készülöttem, és úgy gondoltam, hogy lemegyek, és azt mondom, hogy milyen jó volt nektek, semmi dolgotok nem volt, csak aláírni reggelente. És elolvastam aztán, hogy mit tettek ők, és rájöttem, hogy nagyon nehéz időszak volt az is. Akkor nem volt Covid, nem volt háború, de nagyon nehéz időszak volt akkor is. Úgyhogy átírtam a beszédemet természetesen, és ő is megerősítette, csak úgy, mint professzor úr néhány perccel ezelőtt, hogy ez sohasem könnyű. De nem erről szeretnék beszélni, hanem egy kiváló életmű elismeréseként az ELTE TTK platina oklevelet nyújt át Fuchs professzornak, rektor úr üdvözletével, tiszteletteljes üdvözletével együtt. Nagyon sok szeretettel gratulálok, és ahogy elhangzott, leginkább örömteli és boldog életet kívánok. Egy kis matematikával fűszerezve. Gratulálok, professzor úr.
Köszönjük szépen, dékán úr! Ezzel a ünnepélyes része a mai eseménynek véget ért. Most a matematikára térünk át, angol nyelven. Aki nem érez magában nagy érdeklődést a matematikai tételek iránt, annak megengedjük, hogy továbbiakban ne vegyen részt ezen az ünnepségen, de nagyon köszönjük elnök úrnak, alelnök úrnak, dékán úrnak a részvételét mai ünnepségünkön. Zsolt, most már...
Ladies and gentlemen, after the festive part of this event, we are now switching to the scientific part. The scientific program is made of 5 talks. Each of them is devoted to one of the eminent professors of the Big Five. In the morning program, we will have 2 talks. The first one will be delivered by Professor Luigi Salce, Fascinating Modules over Valuation Domains. This is the title of his talk. Professor Salce, the floor is yours. Akkor lehet, hogy ide vissza.
Thank you. Good morning. Here is the title of my talk, and here is a summary of the points of my talk, the background, the season of the existence proofs, the semigroup Unis R, which is the top of the talk, more applications of non-standard uniserial modules, and the last, the cellular covers of non-standard uniserial modules, and then 1 minute for the conclusion. I have 12 slides after this, and I have also 5 pictures to show you. So I starting my talk. It is a great honor to be here, giving a talk at the Big Five meeting, and it is a great pleasure to meet again László on this occasion, and of course David with Ayla and David. A talk describing the mathematical work of László would take not 50 minutes, but at least 3 days. Moreover, 3 papers on his research work have been already published, the first one in 1996 by Rüdiger Goebel, the second one in 2001 by me, and the last one in 2014, 10 years ago, by Bruce Olberding and Rangaswamy. So for my talk, I selected a topic of module theory that we began studying with László more than 40 years ago, and whose contribution by László continued up to last year. The starting point was in July 79. Here's the first picture. When the University of Montreal organized the Séminaire de Mathématiques Supérieures with László as one of the main speakers. I spent there almost 1 month in Montreal with my colleagues from Padova, Adalberto Orsatti and Claudia Metelli. During a picnic on a lake, and this is a picnic, you can see from the left to the right, I have the first one, then Orsatti, then Mario Fiorentini, it is a geometer, Italian geometer, and László on the right. László proposed me to study what was known about modules over valuation domains, and to investigate this new area, new at least for us. It was the natural development of the investigation of abelian p-groups, which are modules over the discrete rank 1 valuation domain Z localized at a prime P. We already had some joint papers on p-groups, written when I spent 1 year at the Tulane University in New Orleans in 75-76 of last century. So our understanding and harmony in doing research was already tested. So in autumn 1979, we started the new project. And when you study modules of a ring, starting from the beginning, first you analyze the simplest modules. This means the cyclic modules. In case of valuation domains, it immediately appeared of basic importance a class of modules containing the cyclic ones, namely the class of uniserial modules, whose some modules by definition are totally ordered by inclusion. They form a chain, the submodules. Recall that one of the definitions of a valuation domain is that it is a uniserial module over itself, so its ideas form a chain. And also the field of quotient Q is a uniserial module. So I will use always these symbols. R is a valuation domain, and Q is its field of quotients. The torsion-free uniserial modules are either isomorphic to Q or to ideals of R. Furthermore, I made a drawing trying to make a picture of the torsion uniserial modules. They are of the form J sub I. J is a submodule of Q containing the domain R, and I is a non-zero ideal of R. So the gray part represents J sub I. So you can think at Q as a tube. In the middle you have 1, the neutral element, and the circle around 1 consists of the units. When you multiply, you go down. When you divide, you go up. And J sub I, the right top, is a union of cyclic modules of the form R inverse R modulo I. So J sub I is a direct limit of these cyclic modules with the inclusions between the two cyclic modules. I will refer to I as the bottom of the uniserial module and to J as the top of the uniserial module. And we called these modules standard. Why? Since they are what you normally encounter working on modules over valuation domains. You encounter standard modules. The following question naturally arose. Are all torsion uniserial modules over evaluation domain standard? In other words, the question was, do non-standard uniserial modules exist? László told me that also Robert Warfield, a top algebraist died some years ago, faced this question without success. I found in my notes that you told me this, László. Some simple observations showed that in certain cases, non-standard uniserials do not exist. For instance, if you assume that the uniserial modules are countably generated, or that the evaluation domain is almost maximal, a kind of rings introduced and studied by Kaplansky. But soon we realized that to prove or disprove the existence of non-standard uniserials was a challenging problem. Now we must jump 5 years later. When I organized in 1984 a conference on abelian groups and modules in Udine, where I was professor for 3 years. Many people working on abelian groups came to Udine on that occasion, and also Saharon Shelah was attending the conference. Recall that 10 years before, Shelah created a big shock in the community of abelian group researchers with its solution of the weighted problem. Shelah was in permanent search of open problems to solve during the attending conferences. With László, we explained to Saharon the problem of the existence of non-standard uniserials. The day after, he gave us the solution created during the night using model theory and forcing. The non-constructive, highly non-constructive solution was non-standard uniserial modules over certain valuation domains do exist. Even if I was not able to understand Shelah's argument, I don't work in model theory. His proof of the existence, published only 2 years later in 1986, gave to László and me the input to start working on non-standard uniserials, to understand their behavior and to try to find some application. We included this topic in section 3 of chapter 7 of our first joint book, Modules over Valuation Domains, published in 1985. In this book, you find another proof of the existence of non-standard uniserials, which makes use for the first time of a set theoretical extra axiom with respect to the usual Zermelo-Frenkel choice system, I will say ZFC system, and the new set theoretical axiom was the Jensen-Diamond principle. This demonstration with extra axiom was followed by many other proofs. I will give a brief summary of these proofs in the next section dedicated to the season of existing proofs. I think it is useful to give just an idea of how a non-standard uniserial module U may be constructed. The right bottom part describes synthetically. Note that a torsion uniserial module U is the direct limit of a direct system of cyclic modules like J sub I. But if for each R dividing S, so you have R inverse R modulo I contained in S inverse R modulo I, if first we twist the cyclic module R inverse R modulo I with an automorphism obtained multiplying it by a unit, then we embed this twisted copy into S inverse R modulo I, and we obtain, sorry for the technical details, we obtain a different direct system provided the units you use satisfy certain compatibility conditions that you can write here. The direct limit U of this new direct system under certain conditions, roughly speaking, if the domain R has enough quotients which are not complete, is non-standard. A concrete example, if you like concrete examples, here's a concrete example of evaluation domain admitting a non-standard divisible uniserial module. It is slide 1. Consider an arbitrary field F and the field of formal rational functions with coefficients in the field F and the exponents in a totally ordered group gamma, which is the direct sum of omega 1 copies of the integers. Omega 1 is the first uncountable ordinal. And this gamma is totally ordered with the anti-lexicographic order. And let R be the evaluation domain associated with the canonical valuation. There is a canonical valuation denoted by V. So R consists of the element with non-negative value. Then this R admits a non-standard divisible uniserial modules. And this was proved using diamond Aleph 1, assuming the field of cardinality Aleph 1 in our 1985 book, and it was proved in ZFC, Zermelo-Frankel choice, by Ziegler, Martin Ziegler, over an arbitrary field 12 years later in 1997. And before to leave this background section, there is a very important result that I must mention. The first application of non-standard uniserials to a classical open question asked by Kaplansky. The question is every valuation ring commutative valuation ring with zero divisors? Is the quotient of evaluation domain? And László is generous in giving credit to both of us of the solution published for the first time in our 1985 book. But he was, I'm sure, the only author of the discovery of the nice proof of the following fact. If R is evaluation domain and U is a divisible non-standard uniserial module, then the Nagata's idealization of U, called often a trivial extension of U, denoted in this way, R with plus in bracket U, is evaluation ring which is not a quotient of evaluation domain. Recall that the ring, the Nagata extension, is as an R module the direct sum of R plus U, but there is a multiplication of pairs that you can see in the bottom. The answer to the Kaplansky's question was uncertain before László's solution, since the question for local rings has a positive answer and has a positive answer also for certain valuation domains. And now I pass into the second session, the season of the existence proofs. It is a long period of 12 years. After the publication of our 1985 book containing the proof of the existence of non-standard uniserials using the diamond principle and the solution of the Kaplansky's question, the season started of the many existence proofs of non-standard uniserials using different extra axioms of set theory or with the techniques of model theory or finally in the Zermelo-Frenkel choice system. With contribution, here is a list of authors: Scheller, Fuchs, Franzen and Gebel, Bazzoni and me, Paul Eckloff, Barbara Ossowski, and finally Martin Ziegler. I will give a concise summary of the main results. And the season continued from 1985 until Ziegler's paper published in 1997. People interested in more details could read my paper with a funny title, The Boboli Garden of Uniserial Modules, or Chapter 10 of our second book with László, Modules over Non-Noetherian Domains, and the notes of that. The existence proofs. The first two existence proofs I already mentioned, the first one by Scheller and the second in 1985 in our first book. Then in 1987, Franzen and Gebel constructed non-standard uniserial modules over suitable valuation domains, satisfying some countability condition using not the diamond principle, but the weak diamond principle discovered by Devlin and Scheller in 1978. And this weak diamond principle is a consequence of the inequality 2 to the Aleph 1 is strictly bigger than 2 to the Aleph naught, which is obviously a consequence of the continuum hypothesis. Then in 1989, Fuchs and Scheller, in their revision of the Kaplansky's problem, gave a proof of the existence in ZFC, but non-constructive, using the compactness theorem for logic with quantifications, with branches. I don't know what these words mean. That use the technique of transfer argument typical of model theory. Then, in 90, with Silvana Bazzoni, we gave a classification of non-standard uniserial modules into 6 different classes, distinguished by which of their quotients are non-standards. I can escape these. And we proved, using the principle diamond Aleph 1, that all these classes are non-empty. Then Eckloff appeared on the scene in 1992. He developed the transfer argument used by Fuchs Scheller, which allows the transfer of the results on the existence of non-standard uniserials, like those obtained by Bazzoni and me for the 6 classes, the transfer from models of ZFC plus diamond to all models of ZFC. Then, 1992, an important step, Barbara Ossowski gave the first concrete and direct construction in ZFC of non-standard uniserials over an appropriate class of valuation domains. Her construction shows that a suitable valuation domains has non-standard uniserials in each of the 6 classes quoted above, and the proof is constructive in Zermelo-Frenkel choice system, the first one. Then in 1993, Eckloff and Shelah published 2 papers, one in Transaction of American Mathematical Society, and the last one, if I remember correctly, in Journal of Pure and Applied Algebra. And they introduced new tools for the invariance called gamma invariance, gamma of J sub I, for torsion uniserial modules. And this invariance takes values in the Boolean algebra of the equivalence classes of subsets of omega 1, the first uncountable ordinal. This invariance, roughly speaking, measures the lack of ultra-completeness of the factor ring R modulo the annihilator of J sub I. If this gamma invariant of J sub I is 0, non-standard uniserials of type J sub I do not exist. If in the opposite side this gamma invariant is 1, non-standard uniserials exist in both cases of assumption or negation of the continuum hypothesis, but assuming that the domain has cardinality Aleph1, and if this gamma invariant is strictly contained between 0 and 1, the existence is independent on the axiom of the Zermelo-Frankel plus the generalized continuum hypothesis. Finally, the last step in 1997, as I already mentioned, Martin Ziegler gave a proof of the existence of a divisible non-standard uniserial module over evaluation domain, the evaluation domain of the examples that I showed you at the beginning. It is a very elegant and very deep proof, and he uses the first derived functor of the inverse limit. And his proof is presented substantially improved in chapter 10 of our second book modules. And I have here image 3, if you can read. In 1990, we organized a conference of brilliant groups and modules in Bressanone, Brixen, South Tyrol, with Alberto Facchini and Paolo Zanardo, my colleagues in Padua. And we had 9 main speakers. And you can read that 4 of these 9 main speakers were working in 1990 on the existence proof of non-standard uniserial. László, Fuchs, Paul Eckloff, Rudiger Gebel, and Barbara Osowski. So most excellent algebraists were working at that time on this problem. So I pass now to the third section on the semigroup Unis R. R is evaluation domain. So once the existence of non-standard uniserial modules was acquired, with Silvana Bazzoni, we started investigating their behavior in 3 papers in the 90s, finding 6 different classes, as I mentioned, of non-standard uniserials. László joined us in these investigations, and the results obtained with Silvana were reorganized in the 1995 paper titled The Hierarchy of Uniserial Modules over Evaluation Domain, where we deeply investigated this monoid denoted by Unis R. Unis R denotes the set of the isomorphic classes, I will call in short the isoclasses, U in bracket of all torsion uniserial modules U. And the operation making Unis R a semigroup and also a monoid is the functor tor, one of the 4 most important functors in algebra. And without doubt, a crucial and decisive step, in my opinion, in the work made on non-standard uniserial modules was the idea of László of multiplying to such modules U and V using the functor Tor. László introduced this multiplication in his talk at the Abelian Group Theory Conference in Oberwolfach in 1985. The starting point was the formula of the Tor product of two standard uniserial modules that you can see here. Tor ij, j prime, I prime is isomorphic to the torsion uniserial. You take this intersection modulo the product. And as the functor Tor commutes with direct limits, one can extend the Tor product to non-standard uniserial modules. With this commutative operation, Unis R becomes a monoid with neutral element, the isoclasses of Q modulo R. The great fascination that I mentioned in the title of torsion uniserial modules derives, in my opinion, from the structure of the semigroup Unis R, which becomes much more rich and attractive when R admits non-standard uniserial modules. It is impossible to give here a description of the complex structure of Unis R, which is very simple if R is a discrete rank 1 valuation domain. But even for non-discrete Archimedean valuation domain is not simple. So I will recall only some few facts. A central tool in the investigation of Unis R was the use of the Clifford semigroups. Such a semigroup is a union of pairwise disjoint constituent groups indexed by Temit semi-lattice. Sorry for these technical details, with bonding homomorphisms between two different groups. László was colleague in the Tulane University of Alfred Clifford, and Alfred Clifford was the author of two celebrated volumes in the theory of semigroups. And I also met Clifford when I was in Tulane. I was guesting his beautiful house in the Audubon Park, if you remember, the pink house. And in particular, László knew very well Clifford semigroups that in the commutative case, because you can define Clifford semigroups also in the non-commutative, but in the commutative case, these semigroups provide the frame where the torsion uniserial modules, standard and non-standard, found their beautiful argument. I think I can escape technical details on some more questions on Unis R, but if someone is interested in this very technical and complicated structure of Unis R, the results obtained with Silvana and László can be found reorganized and improved. This is a picture that I will explain in a moment. Reorganized and improved in the last 4 sections of chapter 10 of our book of 2001. This 4 sections take more than 20 pages, so it is a very complicated matter. And in the same book, a generalization of non-standard divisible uniserial modules to arbitrary integral domains R with quotient field Q led to the notion of clones of Q sub R, which form a group denoted by group R. The group of clones was investigated by László with Péter Vámos in 2019. It was the last paper of our friend Péter Vámos. And I must explain this picture. This goes back to 1998 after a conference on abelian groups in Dublin, with László, we made a tour in Ireland with 2 cars, and we stopped in a pub, taking a beer or a Coca-Cola, I don't remember. And here we were discussing how to organize the material in the last 4 sessions of chapter 10. I remember we were talking on non-standard uniserials. Now, more applications of non-standard uniserials. I'm sorry that the applications are all inside the theory of modules over valuation domains. We cannot apply non-standard uniserial outside of this realm. The solution of the Kaplansky's problem is certainly the most famous application of non-standard uniserial modules. But more interesting applications have been found in this next slide. Immediately after the publication of our 1985 book, László found remarkable applications to 2 classes of modules lying in opposite directions, indecomposable on one side and super-decomposable modules. Are 2 extremes. A module is indecomposable if it is not the direct sum of 2 non-zero modules. And it is super-decomposable if it has no non-zero indecomposable summand. You can always split into summands. If summand, you can split it into summands and go on. The 2 applications are based on the fact that if you take 2 non-isomorphic, divisible non-standard uniserial modules U and V, there are no homomorphisms except 0 from U to V. Okay? And using the existence of non-standard uniserial modules and assuming the Jensen-Diamond principle, first, László proved that over suitable valuation domain there exist indecomposable divisible modules of arbitrary large cardinality. And this is contrast with what happens for abelian groups. Then László showed the existence of super-decomposable divisible modules as small as possible. This means with countable Goldie dimension. The Goldie dimension is an invariant that measures how big can be a direct sum contained in it. A third application is a generalization of the celebrated Matlis category equivalence, the last row, between the category C, denoted by C, of reduced torsion-free modules over an arbitrary valuation domain which are complete in the R topology, and the category denoted by D of the quotients of direct sums of copies of Q sub R. In a joint paper in 1990 by László and me, we proved that over a valuation domain admitting non-standard divisible uniserial modules, the 2 above categories are also equivalent to the category denoted by D sub U of the quotients of direct sums of copies of U. The last application I would like to mention is a little more technical, and it is to the non-vanishing of the Ext modules obtained by László in 1986 and improved with Sheila in 2003. It is a basic result of homological algebra that I say this because just to explain the next symbols. A basic result of homological algebra, the equivalence classes of short exact sequence 0, A, B, C, 0, with A and C fixed In this case, you have X to V, where you fix V and you fix U. And these equivalence classes form an R modules denoted by, in this case, X VU. And László and Shelah proved that there exist evaluation domains admitting non-isomorphic, non-standard divisible uniserial modules U and V, such that the module of extension X to V, and this is very important for the next session, X to V is a divisible module, and this is easy, but it is mixed. This means that it contains exact sequence with zero annihilators. There is this exact sequence with zero annihilator. This property of X to V of being a mixed module will be used in the investigation of cellular covers of non-standard uniserial modules that I discuss in the next session. So the fifth section is cellular covers of non-standard uniserial modules. Very recent result. The last time I met László, this is a picture made, was in Padova in 2016, 8 years ago, on occasion of my retirement. This picture is taken in my office. At that time, I still had an office in the department. Now, of course, I don't have an office. When László, in 2016, involved me in the investigation of almost perfect commutative rings with zero divisors. And I thought at that time it was our last collaboration 8 years ago. But I was wrong, since non-standard uniserial modules and their cellular covers joined us again last year, 2023. The paper Cellular Covers of Divisible Uniserial Modules over Valuation Domains was published last February 2024, on Forum Mathematicum, with authors László, Brendan Goldsmith, Lutz Stringman, and me. The remark at the end of the introduction of that paper explains the origin of the papers, and I will read these 10 lines of the remark. This paper has had a long gestation period. It started in 2011 with an unpublished preliminary note in which László prompted his co-authors, Rüdiger Gebel and Brendan Goldsmith, to continue to develop the theory of cellular covers for divisible modules over valuation domains. Unfortunately, the note arrived at a time when Gebel was ill and unable to participate in the project. With his untimely death in July 2014, the note remained untouched until 2019, when two of the current authors, namely Goldsmith and Stringman, revived the project and made good progress. They were subsequently joined by Luigi Salce. I joined, if I remember correctly, in February 2022, who succeeded in bringing the project to a partial conclusion. And László was out in 2000 until autumn of 2000, no, until spring of 2023. Finally, the 99-year, it was last year, old László Fuchs reorganized the material, adding more insights and results, and gave his final touch to the paper. And I will explain how László was decisive to complete the paper. So the last a little technical. What is, sorry, if you don't like to read this slide, you can escape it. A short exact sequence of the form 0, K, G, A, 0 with gamma, the map from G to A, is called cellular exact, and the map gamma from G to A is a cellular cover for A if every homomorphism from G to A phi factors uniquely through gamma. So you have a unique endomorphism of G theta, which makes the diagram commuting. Brendan Goldsmith suggested to look when an exact sequence 0, next one, when an exact sequence 0, V, C, U is cellular exact with V and U fixed. You must find the C which makes this sequence cellular exact. Of course, U and V are two assigned, non-isomorphic, divisible, non-standard uniserial modules. At this point, the experience of László was decisive to conclude in a brilliant way the paper, since the property of XUV, the extension module, of being a mixed module mentioned above, provides the right characterization of cellular covers. And in fact, László proved that the sequence 0 VCU is cellular exact if and only if it represents an element of X with 0 annihilator. The final result of the paper is contained in a theorem, so I had to write at least one formal theorem for my paper. This theorem has two items. The first item is in ZFC, and the second item in the next slide is using diamond. First item, there exists a valuation domain R and U and V non-isomorphic, divisible, non-standard uniserial modules such that the sequence 0 VCU0 is a cellular exact sequence for a suitable divisible R module C. And the last slide, using diamond Aleph1, let R denote the valuation domain considered in the first example that I showed at the beginning. For every pair UV of non-isomorphic divisible non-standard uniserial modules, there exists a cellular exact sequence 0 VCU0. And while item 1 provides only an existence statement, item 2, with the full force of diamond Aleph1, states that the desired cellular exact sequence exists for any choice of the pair UV. And I'm on time, and I have 1 minute for my conclusion. And I cannot finish my talk without expressing also in this occasion my deep feeling of gratitude to László, not only because our collaboration was very important, of course, for my academic career, but most important for the passion I absorbed from him in doing research in many different areas of algebra. And I'm sure this feeling is shared by many other mathematicians of different generation. Thank you.
Okay, thank you very much for your talk. And now we will immediately switch to the next talk delivered by Professor Berkes, who is going to speak about the scientific works and achievements and life of István Gaál. Okay, floor is yours.
where are my slides? Yeah. Hello. Where is this? Oh, yeah. When I started preparing for this talk, I also went on the internet to find something about Big Five, and I read into the exactly absurd hits. I don't remember, there was the closest one to this one, some kind of a big shot businessman in South Africa, which is not exactly a big game in Africa, but finally I got into the homepage of the University of Minnesota, and there I find a nice short biography of István Gaál. So he was born in 1924, February, in Budapest. He got his PhD from the University of Budapest under Frigyes Ries and Lipót Fejér, quite a pair of PhD supervisors. And his thesis problem was had origin in the letter of Paul Erdős, a problem which became a prize problem for the Netherlands Mathematical Society, and Gaál solved it, and he published this with Erdős, and this became his first famous paper, the start of his very deep activity in the Diophantine approximation theory. Well, after obtaining his PhD, he served as he went to France. He was an assistant professor at the University of Szeged and then in Budapest, and then he went to the CNRS in Paris, where he worked from 1948 to 1950 with an attaché de recherche with supervisors, among them Jacques Adamar. It's also quite a remarkable bosses in this field. Then Atle Zellberg brought him in the Institute of Advanced Study in Princeton when he was Zellberg's assistant from 1950 to 1952. And then in 1953 became instructor, in 1951 at Cornell University and later at Yale University. And finally he went to the University of Minnesota together with his wife, also a noted mathematician, in 1960. And he came there as an associate professor and was almost immediately promoted full professor, and he worked there for the rest of his career at Minnesota. He retired in 1993 and subsequently moved to Nevada, where he spent the last years of his life, and he passed away on March 17, 2016. So this is a very long career, but to discuss it, some elements of his career, let's go back to the very beginning, almost 100 years earlier, to a famous result of Kronecker, who said that for any irrational number in 0, 1, the fractional part of n alpha is uniformly dense in the interval 0, 1. And it turned out later that much more than that is valid, and by the famous equidistribution theorem of Hermann Weil, but also discovered independently several other people, Sierpinski, Bohl, that n alpha is not only uniformly distributed modulo 1, is not only dense, but is also uniformly distributed. And uniform distribution is defined here. So a sequence is uniformly distributed in 0, 1 if you consider any sub-interval of the interval 0, 1, a, b, and you count up to what percentage of the process is in sequences in this interval. You count up to n, how many terms are there, divide by n, and the sequence is uniformly distributed ud if this fraction go to b minus a. Now, if you are a probabilist, then you will notice immediately that this is also a probabilistic concept if you consider the sequence xk as a statistical sample, an infinite statistical sample. Then this convergence means that the so-called empirical distribution function of the sequence converges to the uniform distribution. And you can measure you can measure the uniformity of the sequence in a quite natural way. This definition due to Hermann Weyl, you simply count, you know, up to n what actual proportion of the first n terms of the sequence lies in B minus A, and then this dn measures how rapid this convergence is. And again, for probabilists, this is the so-called, the discrepancy is the so-called Kolmogorov-Smirnov statistics. So even today, it's a very popular test of non-parametric statistics. For example, to test that if a given sample is coming from independent random variables, you compute the discrepancy, again, which is called the Kolmogorov-Smirnov statistics. And if this lies above a certain critical level, then you reject the hypothesis, and otherwise you accept it. But there are other, but this concept is fundamental in whole mathematics. It has applications in practically every part in mathematics. So by Cox-Mass inequality, which is somehow written in the last row of this slide, shows that if you have a function f of x, and then for numerical integration, you approximate the integral of f of x by the arithmetic mean of in certain intermediate points, then the order of magnitude, the error made by this approximate integration, is measured by the discrepancy. Oops, this is the wrong. Okay. So to compute, so here are a few classical probability number theoretical results. So as we have already seen, then the fractional part of n alpha is uniformly distributed. It's actually true that not to the n alpha n to the r to the alpha any r greater than or equal to 1, but not every subsequence of n alpha. For example, if n factorial alpha is not uniformly distributed, if, for example, choose alpha is of E, then the n factorial times C is very, very close to a the series of A converges very rapidly, and n factorial times C is very close to an integer. It means that the fractional part of n factorial times C goes to 0. So instead of uniformly distributed the interval, it simply converges to the left endpoint of the interval. For some other numbers, if you consider 10 to the n times alpha, the fractional part of 10 to the n times alpha is uniformly distributed if and only if the decimal expansion of alpha is normal. In other words, the density of the digits, all the 10 digits, is 1 over 10. Well, you cannot check this for concrete numbers. It's still, we don't even know that, for example, the decimal expansion of square root of alpha has infinitely many zeros in there. This is one of the very difficult problems. One cannot even measure how difficult it is. Certainly a lot more difficult than anything that probably has ever been attempted in number theory. And there is one more remarkable connection here. And the better the alpha can be approximated by rational numbers, it means that the slower the speed of the discrepancy tending to 0. So for example, how do you measure the approximation of an irrational number by rationals? You can consider, we know that for every rational number there are infinitely many fractions p over q, that the difference of that one is 1 over q squared. This is a famous result of, this is the Dirichlet's result. It's just a few lines to prove it. There are some other numbers that can be approximated better, 1 over q to the c plus 1 when c is bigger than 1, and these numbers are even better approximable, and the smallest such number is called the Diophantine rank of alpha, and it's a famous result in number theory by Klaus Roth that for all algebraic numbers, the C is equal to 1, so these numbers are very badly approximable by rational numbers. And it is quite easy to show that almost all numbers in the sense of Lebesgue measure are badly approximable, and accordingly the convergence to the discrepancies is very small. But there are many other famous applications of discrepancy in number theory or in analysis. For example, there is a famous result of Siegel showed that the stability of fixed points algorithm x equals f of x, the stability depends on also some kind of rational approximation of alpha. If f of x is it has a power series expansion, then this fixed point is stable, which is a natural definition. If the first, it depends on the first term of the power series expansion. If this is less than 1, then it's stable. If it is bigger than 1, then this iteration process is not stable, not even converging. And the critical case is when the absolute value of the linear term is 1, and then that means that A1 is some point on the unit circle, e to the 2 pi I alpha, and the stability depends on the rational approximation of this alpha. So this is a very, very deep result, but it has also applications, very large importance in physics and in classical mechanics. For example, in the three-body problems and in general in the stability of the solar system, where Arnold showed, it's one of the famous papers in the Kolmogorov-Arnold-Moser theory, is that if you consider three bodies, for example, the Sun, Jupiter, and Saturn, and then you can notice that the angular velocity of Jupiter and Saturn around the Moon is about 300 and 120 degrees. And the ratio of these two things is almost 2/5. And the problem that this ratio is too close to a rational number causes a problem of the stability of this differential equation because of that series what you write here. And basically this kind of rational approximation also plays a very crucial role in these famous investigations of Kolmogorov and others on the stability of the solar system. Now, by Cox-Mass inequality, which I mentioned before, then a sequence is n alpha is uniformly distributed if and only if the averages of fk alpha goes to the integral of 0 to 1 again of this Riemann approximating sums converge to the integral. Well, not for all f, but for all functions of bounded variation. So to study somehow the uniform distribution and discrepancy, basically that means we have to study the law of large numbers. The law of large numbers for a very simple sequence of random variables, the fractional part of k alpha, when alpha is a random number, random uniform number in 0, 1. And the question is that to what functions of this very simple random sequence satisfy the law of large numbers. And well, of course, the law should be uniform for all functions is a bounded number of variations. So this somehow, so again, we, in a sense of point of view from a probabilist, is basically we are dealing with the probability theory of a very simple sequence of random variables n times alpha, where alpha is a random uniform number in 0, 1. But the results are, of course, not probabilistic, but number theoretic. So the first one to prove here something remarkable was Hardy and Littlewood in 1915, who proved that the partial sums of k alpha for almost every alpha is n/2. That's the average value, plus a big O of log n to the 1 plus epsilon. And Hinch improved in 1924. This is the same famous year, 100 years ago, when all these great mathematicians were born, that the exact remainder term is log n. Now, this means that these random variables are very strongly dependent. For a normal independent random variable, the remainder term would be square root of n, but the fact that this convergence is much faster, this log n, is the sign of a very very different, strongly dependent sequence, and this probabilistic studies makes it extremely hard, despite the simplicity of this system, and this is where some of the early work of Gaál was concentrated. So Khinchin conjectured in 1923, it's again coming to around this year, exactly 100 years ago, that if f1 is a periodic Lebesgue integrable function, then the averages of fkx for almost every x converges to the Lebesgue integral of f. Now this, for an analyst, well, for a probabilist, this is just like very similar to a strong law of large numbers for the sequence. But in an analyst, we say this looks like is a Riemann approximation sum of f, and Riemann approximated sums do not converge to the Lebesgue integral. So this seems to be a very, very bold conjecture. Well, Khinchin was a very clever man, of course. He knew that. I mean, that was basically the year when this Lebesgue integration and measure theory was basically founded. Well, Khinchin made this conjecture because he said that this would be a very attractive definition of Lebesgue integral in terms of number theoretic definition, just as the limits of fkx for a random x. And actually, there is also a reason that such a thing might be true. For example, if you replace the kx, is 2 to the kx, then you get the result, which is the ergodic theorem, and that is Lebesgue approximation sum. So not this is by the ergodic theorem, then this is true. So the matter is rather critical. Well, anyway, this became a conjecture that became one of the longest open conjectures in 20th century mathematics. It was first decided by about 1970 when it was disproved by Marstrand, and until that point nobody really knew what was really the situation here. The first negative sign was that this is not true was due to Erdős in 1949. I come to a minute to that one. But Erdős at that time still believed that the conjecture is true. He has a famous paper, the conference papers in 1964 when he discusses that and expresses the opinion that this might be true. But anyway, there are, of course, the ordinary laws of large numbers for independent random variables. Well, everybody learned at the university Kolmogorov's law of large numbers, which is actually for square integrable random variables. If you have independent random variables mean 0 and the variance is sigma k squared, then if the sum of the variance is sigma k squared divided by k squared is less than infinity, then we have the strong law. Then we have the strong law of large numbers. This is actually valid for orthogonal random variables. This is due to Rademacher and Menshov. Under the same condition, if you assume that the CKs are orthogonal, or more generally, if the sum of the variance of the square integral of the partial sum m plus 1 to m plus n is less than n, which is somewhat weaker than it's called quasi-orthogonality, then you still have the strong law of large numbers. But this is an optimal result. But it doesn't apply in this situation if you consider, let f be, assume that f in this, going back to Khinchin conjectures, is a square integrable random variable. You expand it to a Fourier series with coefficient ck, and then somehow the covariances or the square integrals of the non-partial sums are estimated in a very complicated way. It's not an orthonormal sequence. If you see at this very complicated sum on the right-hand side, you see that this is some expression in terms of the Fourier coefficient, which is a number theoretic type. The summation is also extended only for all numbers with greatest common divisor d, and somehow, so the question is number theoretic. And under this condition, the Rademacher-Menshov trick goes down, it breaks down, and nothing really works. So this really shows what is the problem here. We have a very simple structure, but somehow the covariance structure is totally intractable in a certain way. And so you need, I mean, you need here a law of large numbers, which is much better than those of Kolmogorov and Rademacher-Menshov, which applies on this very irregular structure. And this is the result what he did with Koksma in 1950 in the proceedings of the Royal Dutch Mathematical Society, which is probably the basic law of large numbers in arithmetic, so number theory, the Gaál-Koksma law of large numbers. And this might be, well, arguably one of his greatest achievements, but there are many other interesting things here. I formulated here in all details, except that I translated into English. It's extremely complicated, but somehow to get an idea of what is going on here, you have some functions, u, nu, these are the variables, and you consider the partial sums, fmn from m to n, and the basic assumption is that let px equal to 2, that the integral of the partial sum from n to the square is bounded by some very complicated expression. This is what in orthogonality simply equals to n, but instead of orthogonality, you have some very complicated conditions. And again, what you, instead of going into technical details, you may notice that the size of these intervals are 2 to the n, and somehow the individual elements are divided by n. So these are basically makes an assumption on dyadic blocks of this sequence. So 2 to the a times 2 to the k plus a plus 1 times 2 to the k. And this is exactly what Rademacher and Menshov did. So somehow they proved the famous convergence theorem by operating with this dyadic building block, so to say. But they did the easy way to applying the Cauchy-Schwarz inequality, using simply for that one, and that somehow led to the result and also Kolmogorov's result. But now if you have, somehow if you treat these things in a completely different way, then you can get, with proper handling of these dyadic blocks, you can get a better result, which is actually the functions as a strong law of large numbers in number theory. And they actually did that one, so an immediate, well, not immediate, but it's an easy corollary of this Gaál-Koksma law of large numbers is this famous result for Gaál and Koksma, 1953, as far as I remember, which gives basically the solution of this, almost the solution of the Khinchin conjecture. So it says that this f is periodic, square integrable with Fourier coefficients ak and bk. And then if you assume that the sum of ak squared plus bk squared, the convergence is exactly the second moment, is the square integrability. But instead of assuming the square integrability, you have an extra factor here, which is called in analysis a Weil factor, sigma minus 1 to k as a factor there, which is the sum of the reciprocals of the divisors of k. I mean, the sum of 1 over d for d less than n for all numbers up to n is log n. This is the harmonic series, but you only summarize here only for the divisors of n, which is a much smaller number. And it turns out that this function here, the sigma minus 1, is not log n, but is actually less than log n. And even that is a crude upper estimate. For example, if n is a prime, there are only a prime or very few prime factors, then this sum has only 2 terms, so the partial sum is not log n, but 2. So basically, this factor here, what you have is even in basic definition, is extremely slow, but most of the time is practically bounded. So with basically with a condition which is just a little bit harder, a little bit more than L2 condition, we have the Strong-Love-Large numbers, and so under this little extra condition it's practically true under L2 condition. And this explains that why it was so difficult to decide it. There is a counterexample, but because the law is almost valid, one needs some kind of extraordinary clever construction that was done by Marstrand to disprove it. It's almost an impossible thing to do. Well, Erdős said, as I said, he proved in 1949 that for a subsequence, if not nx, but there is a integrable function, and such that it doesn't, the Hinchin's conjecture is not false, but for a subsequence it is false. And since passing to a subsequence makes the behavior of the sequence is generally better, if it fails already for a subsequence, then one might guess that it fails to the original one. But at any rate, Marstrand proved in 1970 that the conjecture is false, and so, but then it's a very complicated paper, Marstrand, and it's difficult to understand. Bourgain gave 1988 another counterexample, an existence proof is using metric entropy theory, which is a modern area, was that in probability theory, also going back to Kolmogorov and Sinai. And using that technology, he proved that, he showed that there is a counterexample, and it also said that, he also conjectured, he didn't go to detail, Bourgain pointed out that this condition that AK squared BK squared times this sigma minus 1K is, this log-log condition as he formulated is not far from optimal. He never said what it means that it is optimal or not far from optimal, but it turned out to be not only not far from optimal, but actually is optimal. So in 20 years later with Michel Weber, using Bourgain's proof, and it was probably there all the time, but he never bothered to look it up, it turned out that this condition, this Gaal-Koxma condition, AK squared plus BK squared times sigma minus 1K is actually optimal in the sense that if you change the exponent of sigma minus 1K to 1 minus epsilon, then this condition is not anymore sufficient for the Strong-Love-Large numbers. So that means that not only this Koxma's condition is optimal, this means that even the theorem itself as a general law of probability theory is I would say, in a certain sense, is the ultimate law of large numbers, even a number theory and whatever is, I would say, is really certainly an immortal contribution to mathematics or number theory or probability theory. It is very hard to distinguish between these things. The year 1924, when these concepts were introduced, these three sciences were basically the same. Probability theory didn't exist at that time. It was used, I mean, the Rademacher functions were, some are used as independent random variables, and this, of course, the law of large numbers by Borel was also a number theoretic statement, and then it was only in 1933 when all these different directions were introduced and crystallized. Now, to go a little bit further, then, of course, there is another way to approach the law of large numbers. Instead of proving that the averages of fkx tend to 0 almost everywhere, it suffices to show that instead of considering the averages using the Kronecker lemma, it suffices to prove that the sum of 1 over k fkx converges converges almost everywhere. So in other words, we get to the problem as that let f be an integrable, okay, let me square integrable function, ck is some coefficient, f is a periodic function. What do we know about the convergence of sum of ck fkx? Well, if f is the trigonometric functions, then this is well known. This is the standard Fourier series, and by Carlson theorem, one of the basic theorems here, it's a very deep result. If a function is in L2, then the Fourier series is almost everywhere converges. In other words, if the sum of ck squared converges, the sum of ck sine kx is almost everywhere convergent. Now, this is 1966. It's a very hard theorem, and I think even today, almost 60 years later, there is no really understandable proof of that one. So typically, this is the topic of a semester course in harmonic analysis. And this problem, what we are discussing here, is that sum of ck fkx is an even harder one. So what happens if instead of the sine functions we have a general periodic function, but the results are not the same. So in this generality, Carlson theorem is not valid. In this generality, it was shown by Aurel Windner, who is also a very important player in this whole uniform distribution theory, Diophantine approximation. Windner proved the following absolutely beautiful theorem. So if you consider FB some kind of Fourier series, sum of AK cosine kx plus BK sin x, then sum of CK FKX converges in L2 norm. Not always everywhere, almost everywhere, but in L2 norms. If and only if you consider, if you build a Dirichlet series, AK k to the minus s or bk k to the minus f, the Dirichlet series with the Fourier coefficients, then this Dirichlet series converge on the whole half plane. Ries is greater than 0, and they define a bounded functions there, both of them. So what does it mean? This shows that this problem is basically a problem in number theory. And if, for example, f is the fractional part function, then the Fourier series, the Fourier coefficient is 1 over k, and then this Dirichlet series ak k to the minus s becomes the zeta function shifted by 1. So in other words, if you want to check convergence, you have to check whether the zeta function on the right side of the line s equals 1 is bounded, which is of course not. It has a singularity, is s equal to 1. So this shows a counterexample to the of this relation in this very simple case. It doesn't show actually that it's almost everywhere divergent. This was a big problem. It shows that it doesn't converge in L2 norm. The fact that it was actually diverges, this actual sum was proved by Nikishin in 1970 in another very famous paper, which also got a Salem Prize for that. So these are very, very hard problems. So here we are dealing with the almost everywhere convergence from this one, and again it's very easily seen that this is a number theoretic problem. So if you consider such an f is a given Fourier series, a square integrable, then there is a quite famous formula of Fresnel and Landau that the integral of fmx, the correlation of fmx and fnx is a fraction which is the greatest common divisor divided by the smallest common multiple of n. It's called, in other words, and equality. This is true for any function of bounded variation, and it has equality for the fractional part function. So the correlations of the fractional part functions are exactly of the GCD expression Mn, greatest common divisor divided by greatest common multiple. And if you, here is the proof, actually, what I said. It's such a simple statement. If you expand f of f and f is Fourier series, then fmx is you have to multiply all coefficients with m, you have to multiply all coefficients with n, then you get the sum of two trigonometric series. But because of the orthogonality of the trigonometric functions, only those terms are non-zero in this one when km equals ln. It means that km and ln are equal. This is a common multiple of m and n, so it's already in this trivial sum immediately the greatest common divisor as common multiple appears. And if you compute then the square integral of the partial sums, then you get here such a thing which is called the GCD sums. So you simply have to add up along a subsequence the NKNL divided by NKNL, and the question is how big are these sums, these GCD sums? And this is the field when Gaal's other result, and perhaps this is his most famous result of this GCD sum. Well, I formulated here the GCD sums in a little more general way. Well, not only of these fractions, but you raise it to the alpha's power. The case of original GCD sums is when alpha is equal to 1, and Gaál proved in 1949. This is his most famous paper, when he proved that this GCD sum is less than n log n square, and this is sharp. It's a very remarkable number theoretic statement. If you just try any sequence, so normally this is n. The order of magnitude is n. Adders proved that is always less than n times log n, but this was not true. If you consider the square phi numbers, then you get n times log n, but this is only a first power of log n, and the real truth is log n square here, and that's what Gaál did. It's a very complicated construction. If this started a whole theory of these general GCD sums, and the final result was done by Sijp. Christoph Sijp is a great Norwegian number theorist, and so in the case alpha equals 1 is log n square, and alpha is between 1/2 and 1, you get another expression. This is optimal, and the critical case we are going to see that is somehow related to the Riemann zeta function is the case alpha equals to 1, and Bondarenko and Sijp proved a lower bound for this generalized GCD sums. But let's go back again to the case alpha equals 1. We have seen that if you consider the fractional part function, that the orthogonality of the functions are not orthogonal, and the L2 norm of the partial sums is not n, but n times log n square. So there's a log n square, and that, of course, suggests that the analog of the Carlesson theorem for this general sequence is not sum of ck square converging, but ck square times log k square converging. It's a very logical conclusion, and it doesn't seem to be particularly challenging. Well, of course, it's challenging because the statement is starting from first principles, is the magnitude of the Carlesson theorem. But it looked a very reasonable project, and in 1915 or 2015, I started to work on this problem with one of my PhD students, Christoph Eisleitner in Graz, and of course we didn't get anywhere. I mean, it's very difficult to do something on the magnitude of the Carlesson theorem, but then Sijp appeared on the scene, and he proved, and he noted that if instead of the Gaál sums, you consider the generalized Gaál sums with alpha very close to 1, so 1 minus 1 over log n, then a sharp bound for this generalized GCD sums will give you the upper bound in the Carlesson theorem. And then it turned out so, and then after with some more steps, it turned out that this will give you the solution of the problem, of this Carlesson problem for generalized functions of bounded variation. And here's the theorem. Let f be a periodic function of bounded variation, and let ck be a sequence so that ck times log k to the gamma is less than infinity. Then if gamma is greater than 2, not equal to 2, but greater than 2, then this sequence is almost everywhere convergent. And if gamma is less than 2, this is not true, and the counterexample is precisely very easy counterexample, the fractional part function. Now the latter part we actually proved, so using this Selbst-type estimate, the result for gamma equals 4 in 2015, and then Levko and Radziwill from the UCLA came in 2015-7 and proved it's not only 4 but actually 2 is valid. So this gives the solution of this problem. And you know, it's actually the real depth in this argument is where the analytic part is not particularly complicated. The great thing is that to estimate these GCD sums with alpha is very, very close, less than 1, but up to less than close this one that SAP did. And then somehow, in other words, this kind of great concept of GCD sums, which is pretty much due to István Gaál, is somehow leaves really quite spectacular and deep results in analysis too. Another word of this one, if this general GCD sums, as I said, that Bondarenko, a young Ukrainian mathematician, proved a lower bound for the case alpha equals 1/2, and for these general GCD sums. And this gives now the best known lower bound on the growth of the zeta function on the critical line, 1/2 plus 1/2 plus IT, not 1/2 plus T. What I wanted to say, we already know from Wiener result that convergence of this series is related to a Dirichlet series, right? So the connection between this convergence problem and analytic number theory is quite clear, but this one shows this a very spectacular way. So a lower bound for these GCD sums provides, and this is the best known lower bound for the growth of the zeta function, is that it grows at least by practically the exponential of square root of t, square root of log t divided by log t. I don't want to go into technical details. The improvement, this is a very old problem, and the previous result was 50 years ago by Montgomery, and the only difference is the log 3, a 3 times iterated logarithm. So this part of the word is, the improvements of these mathematical theorems are very minimal, and they are very deep. But at first, we could say that Gaal's work was instrumental to describe also basic questions in analytic number theory. And now, as a probabilist, I would like to return to something which is also due to Gaál. There is this famous numbers, which I will discuss this before. There is a very serious, a very interesting number in the last line, which is a square root of an irrational number. I tell you the story with that. So the law of the iterated logarithm is due to Khinchin in the year 1924. It was really a magic year in the years of 1924, exactly 100 years ago. So Khinchin, so if you consider if you flip a penny and then you count up to then how many heads are tails, and then the ratio of the heads goes to converge to 1/2. This is just the law of large numbers. And the question is how rapidly is, the question is how far is the number of heads up to the point n differs from n over 2. And Khinchin solved this in 1924. It shows that the precise order of magnitude of the difference of an minus n over 2 is the order of magnitude of square root of n log n. Square root of n is just how the usual thing by the central limit theorem, but it's a little more than that. And they also determined the precise constant there. Now, at that time, in 1924, there was no such a thing as probability theory and independent random variables. This model did not exist. So Khinchin formulated this result in terms of the Rademacher functions, or if you want, the dyadic digits of a random number in 0, 1. So if you consider the Rademacher functions R and T, the signum sine 2 to the nx, then the partial sums of this these are actually independent, identically distributed random variables on the probability space 0, 1 with Lebesgue measure. That was not a typical case of a probability space at that time. So this is the way Hinchin formulated it. But then, of course, he raised the question, what happens if you forgot about the signum and you consider simply the fractional part of 2 to the nx instead of the signum? Well, the signums are Rademacher functions are +1, -1 valued function, but if you forget about the signum, then you get sign-type functions. And he conjectured that that also it will be valid for that functions, but this turned out to be a much harder problem. It was finally Salem and Zygmunt, who were obviously the most prominent harmonic analysts at the time, proved in 1950 that if you consider, for example, they proved that if you consider a sequence nk which goes exponentially, then the sign functions, not the signum side, the sign functions satisfy the upper version, upper half of the law of the iterated logarithm. But they couldn't get the lower bound. But this is a precise result, exactly the Limsup and Salem and Zygmunt could not prove the smaller than 1 inequality. And the reason is a very trivial, you know, very simple one. Everybody might remember the Borel-Cantelli lemma, which says that if you have independent events, then either with probability 1 infinitely many occurs, or probability 1 so only finitely many occur. And the necessary and sufficient condition that infinitely many occur is the sum of the probabilities of these events is divergent. This is very easy, everybody learns in a course of probability theory. But these functions are, the upper bound is okay. For the upper bound, upper half, you don't need independence, and that was very good for Salem and Zygmunt, but for the lower part, you need a Borel-Cantelli lemma for dependent events, and around 1950, it was something is an absolutely new thing. So it was finally Erdős himself, and then in Erdős and Gaál, he finally proved that the lower bound is actually 1. So these sequences are not independent, but still the Borel-Cantelli lemma works for these events, part of that one. And so the Limsup is equal to 1, which means that but they still did not determine, the question remained open, what about the discrepancy of 2 to the n to the alpha? The discrepancy 2 to the n to the alpha is a supremum, so it's stronger than for individual x. It shows the uniform upper bound. And it was it's another very famous result of Gaál in 1963, the first time he proved that the discrepancy of the sequence 2 to the n alpha is again square root of log n divided by n. But Gaál could not determine the constant. And the constant is very difficult to determine because of this dependence, the dependent structure of that one. And this problem was solved. It was 1963. The precise constant was determined in 2008. It's almost 50 years later by a young Japanese, Katushi Fukuyama, who showed that the constant here is the biggest, you know, the constant Limsup there or whatever is not 1 over square root of 2 as in the classical case, but square root of 42 divided by 9. And that was a you know, hotly contested problem. Walter Philipp in 1971, he was the first who tried to prove that. He proved that the Limsup was square root of 48 divided by 9, but his argument was wrong, and it took another 40 years to get the constant. And Fukuyama made, he did, instead of 2 to the n, you can consider 3 to the n, or generally a to the n, and he proved that for any a, this Limsup, this optimal constant, is the square root of a rational number. It's a very, very strange thing. You can write down the Limsup value is a sum of it's an infinite sum of rational numbers. Now, to decide whether the sum of an infinite series is a square root of a rational number is a rather bold thing, and it's still open. It's still open, but he computed it very different numbers of value. Okay, so square root of 42 over 9 if you get 2, and square root of, if the number is not 2 but 12 over 7, then he got this monster number here. And actually his original version was the value of a sigma 3 over 2. 3 over 2 is a very nice little number, and he got it. And he submitted his paper in the Acta Mathematica Hungarica, and it caused a panic there because the result is the square root of a number which have 50 digits up and down. And now you cannot publish such a result, because for typographical reason there is no way, I mean, to put this one. So Fukuyama made a very clever deduction, your artifaction, but even the numerator and the denominator write it in two lines. So this was the first one, and I remember I was a referee for that paper, and József Szabados sent me this paper with the question that, well, what should we do with this paper, and then should we reject it? I mean, it was obviously it looked like a joke or a nonsense. But it turned out to be not a nonsense, so finally it turned out this was all nice, and then somehow I came up with another special case in the same paper, and the author was politely asked to submit his paper with this other number and forget about this thing. But again, this conjecture is almost a Riemannian type thing. It's something like an impossible generality. There is no algorithm to decide if an infinite sum is a square root of a rational number or not. So it is still open. But this is the one, and I think Gaál still have seen that. I don't know. So he must have been happy, you know, that this little, you know, this tree what he planted, and then it grew up in such very, very beautiful asses. And on this note, and I think I will stop my result and let everybody think that they have lunch here. Thank you.